George Hathaway, he's a professional engineer who's lucky enough to own and operate his own lab for testing exotic claims. And if you remember, several years ago, there was a claim of a gravity shield from Podkletnov. His lab was one of the ones to put out the first peer-reviewed paper of experimental results on that, which unfortunately it did not work. But he does things like that. I asked him to come here because of there was so much press about the EM drive and things like that. I wanted to make sure that in this context that the experimental standards of what it takes to get defensible results was at least addressed before any of that came up. So that's why he's here.
Thanks, Mark, and thank you all, and thank the organizers as well as all the Tau Zero folk for inviting me here and listening to what can be an extremely boring presentation. Most of the stuff, or the guts of what I want to talk about that is most germane to what Mark was saying has to do with testing and measurement of very small thrusts and very small forces and very small energies. And those kinds of tests are fraught with pitfalls and difficulties and measurement concerns. And at the end of the talk, I will go quickly through that list because that's probably the most boring part of the whole thing. But in fact, it's the most vital for people who are trying to validate, confirm, test novel and unusual and exotic propulsion systems, or thrust systems for same. I would prefer also, if you're taking pictures of me, that they don't appear on the internet. That's one of my little caveats. I'm one of these rare persons who want to make it really difficult for Googles and Amazons and others to locate me by my face. So if you do take pictures, go ahead and take pictures, but don't put them on the internet if you wouldn't mind. Thank you. As I say, the thrust of the presentation is in pitfalls of measuring, but before that, and since it's moving ahead toward lunchtime, I will start with something more along the lines of the philosophy or the art of measurement. And it just so happens that a couple of days ago, a seminal paper on measurement techniques and especially uncertainty in measurement was published in Review of Scientific Instruments. And I'm going to take a few moments to paraphrase that paper for you and make some comments with regard to that paraphrasing, which are relevant to the kinds of things that I've been doing. As Mark said, I am, I guess, one of the rare persons who are able, through a long history of publishing some rather unusual, in some rather unusual areas, to have attracted some funding that allows me to operate a lab independently of any institution, any government agency, or any other impediment to impartiality. And so I'm extremely fortunate to be in that position, and I hope to be able to maintain that position. Our company used to be called Hathaway Consulting Services. It's now being changed to Hathaway Research, and eventually you will find a website which will be coming on stream in, I hope, a couple of months. So if we can we? Yes, we can. The publication I referred to in Review of Scientific Instruments is this one, and it talks about, as I say, measurement uncertainty in particular. And I'm going to go through a few of the quotes, as I mentioned, which maybe you might find some relevance in terms of of your ability to assess the nature of measurements that need to take place when you're measuring these thrusts and forces on exotic and new inventions that come your way. So they may not come your way. They usually come to me first. And then if I vet them, then they may proceed to further development. I'm the guy who usually gets the wacko, the really weird, the most bizarre, exotic kinds of energy and propulsion proposals, and I need to know how to measure things with reasonably great precision over a broad spectrum of possibilities. So we can start with taking a look at some of these quotes and see how they may be relevant to the kinds of issues that I've come across and have been presented to me. A definition of measurement, and which you can read yourself, and the quote is there from the paper, and this is my little summary of it. The talk that I'm going to present right now will highlight measurement issues which factor into the evaluation of uncertainty. And of course, one wants to be as certain as possible about the efficacy and the validity of a new force measurement leading to a possible propulsion system as possible before one makes a decision about which way to go. Properties of interest of a measurement regarding a measurement are threefold. They can be either quantitative, ordinal, or qualitative, as you can read there. And the properties that are of concern to the measurement of small forces and thrusts and also power systems are typically quantitative in nature, and that's what we'll be concentrating on. Okay, let's move it. And the results of measurements are not just for the happiness of the physicist or the engineer. They're to aid in decision making. What is it that we're going to do with the measurement? What are we going to do with this thing that we've got in front of us? We're going to make decisions as to whether we're going to make further measurements. Are we going to attract funding? Are we going to scale up? Are we going to shut the whole thing down because it has become completely obvious that there's no hope for this particular object or process? So decision making is the real reason we're making measurements, and why estimates of uncertainty are so important. Continuing with the quotes from this paper, not only the measurement method, but also the kinds of instrumentation and the applications of correct instrumentation to the problem needs to be, as they call it, fit for purpose, and have the lowest uncertainties. And that's really rather difficult under a lot of situations, especially when you are presented, as I am, with systems that are not conventional. That's what my job is, looking at unconventional and weird situations. So I have to be prepared to be able to adapt conventional measurement techniques to rather unconventional systems. And so I have to have, and I'm fortunate to have, a suite of measurement capabilities and systems that can be adapted to a large range of rather unconventional approaches. Let's see. And that is basically captured in this next slide too. The choice of appropriate instrumentation as well as the knowledge of the characteristics of the instrumentation is vital. So you would not want to measure the luminosity of a light bulb with, let's say, a resistance meter or something like that. You want to apply the correct kind of instrumentation to the job at hand whilst knowing what the characteristics of the instrument are. So you're not measuring outside the characteristics, you are applying the correct device for the job. And here's an interesting quote from a chap named Bell that is quoted in the paper, and characterizing the uncertainty is basically twofold. How big is the margin of error, and how bad is the doubt about that margin? So you often hear statements like, I am confident that this measurement is plus or minus, let's say, using percentage, 1.5% with 95% confidence. So there are basically two sort of fundamental aspects of stipulating and stating a measurement that is relevant to what you're trying to do, to communicate. And that's talked about here. Measurement uncertainty can be calculated in all sorts of ways, and you hear about them all the time, and even in commercial considerations, but they have to be factored into this decision-making, ultimately decision-making process. And very importantly, measurements themselves are of fascination, I guess, to the measurer, but they have to be transferred. You have to be able to make sure that the measurements you're making are understandable and comprehensible to someone else along that decision tree. And so it's very important that one is able to put into language that is accessible to the succeeding persons or person that is on the decision tree, that they understand exactly what kind of measurement you're making. Especially true when dealing with rather unusual or these so-called exotic technologies, when a lot of folk that you might come across or that come to you with crazy propulsion ideas speak in language that is not understandable. In particular, they talk about various weird energy flotations or crystalline energy or esoteric things like etheric energy or that kind of stuff. That's really difficult to translate into some kind of useful and understandable language. And unfortunately, I come across a lot of that stuff. So anyway, I will highlight a few of the things that I've been involved with, some of which you've heard about, some of which you haven't, and from a long list of exotic propulsion and force type experiments. I've culled a small list here. I've been doing this, by the way, since 1979, and I've seen a large whack of crazy ideas, both in energy production as well as force production, or claimed energy and force production. You've seen or you've heard various discussions about or mentions of Podkletnov, and I'll show you some pictures, by the way, very soon, so to keep you awake. There's Roger Scheuer's EM drive or M drives, and Jim Woodward's Mach effect. We'll talk about, highlight in a sec, but probably haven't heard of Peter Greneau and his son Neil. Let's see if we've got a slide of Oh, before we do it, here's what happens, or what has happened. And there's my daughter many years ago getting excited about STEM sort of things, although she's not involved in that at the moment. And when things get too excited in the lab, things tend to collapse. Anyway, there's Dr. Greneau there, and he is shooting water from a water arc cannon, he called it. And this device was basically a steel cylinder that had had electrodes in the bottom. Very sharp, large current was passed from a capacitor bank, and water shot up. He thought that, in fact, there was a particular explanation for what he measured as being an over-unity idea. Namely, the kinetic energy in the water that shot from the barrel was greater than the energy stored in the capacitors to make the charge in the first place. And he didn't understand what exactly was happening at the right down in the barrel, because it was obvious that when you use very simple momentum calculations, and that it turned out that yes, there was 10-to-1 energy gain or something like that. Well, thanks to Professor Higgins, who happens to be in the audience at the moment, plus some experiments I did, we proved that in fact what was happening at the arc was completely different than what he had expected, and what he used as the basis for his calculations of over-unity. The way this might have been used as a propulsion system was pretty simple. It's the expulsion of water or other fluid as your countermass, and if there was an energy gain somehow, then it would have been a potentially useful propulsion system. Well, that didn't work. And then you noticed on that list before there was something called gyroscopic propulsion. We've investigated many claims of gyroscopic propulsion or force rectification, and this is a rather substantial unit. That's about an 8-inch diameter, high-speed spinning, forced precessing gyroscope. And it was super instrumented with force gauges on the bottom and all sorts of laser distance devices, checking devices, and yet it was constrained to a base. And there was an interaction between the gyroscope, which they were hoping would show a weight loss, and the floor that it was mounted on, but that didn't seem to matter them. It didn't seem to bother them. We made a small device here which got rid of all of the junk down here and allowed us to make a free-floating, unconstrained device, doing various tests on that little model, and proved that a simple version of the device under test could show the effect, or could show whether the expected effect had any validity. And unfortunately it did not, as I'm sure most of you have been thinking in your youth perhaps about, wow, does a gyroscope possibly give us some anomalous thrust like Hathaway and others have claimed years ago. And as far as this particular set of experiments is concerned, no. Podkletnov came to our lab on 2 occasions and verified that, in fact, the discs that we were making in-house would work as a gravity shield in the apparatus that we had made, that I had designed. And there's the liquid helium insert with some of the electronics beside. I'm sorry about the quality of the pictures, but they're obviously Polaroids. And There's Eugene himself right there, taking a look at some early experiments in the lab with non-spinning superconductors, and there's various other pictures of the setup. We then duplicated his system as closely as we could under his guidance, and got null result to a measurement capability 50 times better than what he had published in his 1991 paper. We published this about a decade later in Physica C, and that publication is available if you wish to see it. A lot of people have wondered about the so-called gravity beam experiment of Podkletnov. We are the only other group that has ever, as far as I know, constructed the so-called gravity beam experiment of Podkletnov, partially under his supervision as well. And there's a picture of it. There's a superconductor right in there, and it's between 600 kV Van de Graaff, so it's about a little over a megavolt system, and we did not see the effect that he was claiming. Otherwise, I probably wouldn't be here. I would be consulting with some rather well-heeled investors. There's a picture of Roger Scheuer's EM drive or M drive, fraught with all sorts of difficulties in measurement because of offset centers of gravity of various things that are, like coolant is moving around and things like that. And now Sonny White and others you might have heard of have produced a publication that has gotten people rather excited, and unfortunately the excitement may be a little premature because I wrote an article for Tau Zero, which you may read about, where I claimed that they were suffering from a very bad case of confirmation bias, and that you can go into that yourself. See, how are we doing here? So there's Jim Woodward and his device and his Mach effect thruster. Just a picture of him in his lab. The point I want to make about all this is that, or the points that I'd like to make, let's see if I've got the, there's our version of the Woodward test chamber. This is our chamber. The lessons learned from those 5 examples are summarized here. Consider, in the case of Greneau, in this case, consider all possible relevant explanations for what you see or what you measure. Don't just assume that you have one outstanding explanation for the apparent or claimed thrust that you see. Design the simplest measurements. Remember that very simple version of the gyroscopic thrust device that will validate or not the claims of the inventor, and ensure sufficient information is available. For instance, in the Podkletnov case, we had to make a lot of assumptions because, I can talk to you about that later, there is, Podkletnov was only a small part, he said, of a much larger scheme to make his devices. He had electrical engineers and others, he said, but we could never find them. So beware of confirmation bias and concentrate on claims backed up with a reasonable theory. And that is, I'm putting in a plug for Jim Woodward. In fact, he has what I would consider a reasonable theory. It's not, maybe not a perfect theory, but a reasonable theory on which to base further experimentation. And now, get into, in the dying moments here, the actual meat of the presentation. But it's so pedantic that most people fall to sleep after the first couple of slides. But for those engineers and physicists in the room who are beset with questions about the the validity and the capability of their instrumentation and where measurement is in their decision-making process, they have to be aware of a number of concerns. And I have created this small list of measurement concerns for your edification. They are broken down into these areas, and just for fun, I'm going to go through them. There's a few thermal effects that you have to wash out. There's some buoyancy concerns. There's concerns about measurements under seismic and vibration issues. Even diurnal and gravitational forces can mess up your measurement of really small forces. There's a few that typically come up in even Sonny White's, in any test that you're doing in vacuum. You've got outgassing of materials, you've got slow leaks. All of these kinds of things will impact the kinds of very small force measurements that you can make and can count on. You have to take care of, for really, really precise measurements, Coriolis type forces. Magnetic moments, I don't know whether you can see, can't see from there, whether it makes any difference or not, because I'm going through it so fast. We've been doing a lot of work as you can imagine, with Podkletnov and other related cryogenic tests, and it's really difficult to make valid force measurements in cryogenic systems, especially when there are liquid cryogens around. So you'll find all these effects and concerns about measurement in the paper that will be presented. So that's why I'm not going to beat on any particular ones, but I'm just showing you the magnitude of the number of concerns that you should have when you are designing a test campaign and want to make sure you have dotted all the I's and crossed the T's with regard to measurement. It keeps going and going. A lot of people don't realize how leaky, quote, Faraday cages are. Lots of couplings between electromagnetic effects and any movable masses. Grounding problems, ground loops plague measurement systems. And I mentioned a whole bunch of them there. Gradients, pooled charges, it goes on and on. Then that doesn't even cover instrumentation issues, which are things that you have to take account of as well when you're making sure that your instrumentation is correctly aligned with what you're trying to measure. And there are signal analysis issues, and that's a very short list. And the use of dummy masses and test masses as controls. Have to take account of how you're doing that, how they're matched to the experiment. And finally, I'd like to acknowledge the folk who have helped me put together that list of concerns, and you can read them there. Anyway, thank you very much.